Ever wondered what gives cinnamon its kick, or vanilla its sweet, comforting scent? Well, the answer is hiding in plain sight, in a fascinating family of chemical compounds. Today, we're going to dive into aldehydes and ketones, the secret ingredients behind some of the most amazing flavors and essential materials in our world.
Okay, let's start with a little riddle. I want you to think about the warm spice of cinnamon, the aroma of vanilla, the scent of a perfume, and then think about something like industrial solvents or plastics. What on earth could possibly connect all of these things? They seem totally unrelated, right?
Well, it turns out there's a secret connection. All of these things, from the natural molecules like vanillin and cinnamaldehyde to industrial workhorses like acetone, they all share a fundamental chemical feature. It's this tiny, specific arrangement of atoms that gives them all their unique and really powerful properties.
So, what is this secret ingredient we're talking about? It's a little thing that chemists call the carbonyl group. And this small but incredibly mighty bit of chemistry is the absolute star of our show today.
A carbonyl group is, at its heart, beautifully simple. It's just one carbon atom attached to one oxygen atom, with a double bond. That's it, a C double bonded to an O. But don't let that simplicity fool you. This little structure is one of the most important players in all of organic chemistry, and we're about to see why. Now, you've got to look at its shape, because this is the key. The carbon atom is what we call sp2 hybridized, which is just a fancy way of saying the whole group is flat. It's a flat trigonal shape. And because it's flat, it leaves the top and bottom totally exposed, making it like a perfect landing spot for other molecules to come in and react. It's a real hotspot for chemical activity.
And look, you don't have to take my word for how important this is. Our source material puts it perfectly. These compounds are absolutely vital. They are literally the building blocks for countless materials that define our modern world. So you can think of the carbonyl group as the head of this big, diverse chemical family. And today, we're focusing on its two most famous members, aldehydes and ketones. Let's get to know them and see what makes them different.
So what's the big difference? Honestly, it all comes down to location, location, location. In an aldehyde, that carbonyl group is always at the end of a carbon chain. It's bonded to at least one hydrogen atom. But in a ketone, that same carbonyl group is sandwiched right in the middle of a chain, bonded to two other carbon atoms. It seems like a tiny detail, but it completely changes their chemical personality.
Okay, now that we've met the family members, we need to know how to talk about them. And in chemistry, that means learning their names, a system we call nomenclature. But don't worry, it's actually pretty logical. The official naming system has this awesome, simple trick. If you see a chemical name that ends in al, you know you're looking at an aldehyde. And if it ends in 1, you've got a ketone. So al for aldehyde, 1 for ketone. It's a super handy rule of thumb.
And you can see that rule perfectly right here. You've probably heard of formaldehyde, right? The stuff used to preserve things? Well, its proper name is methanal. See that al at the end? And pretty much everyone knows acetone. It's in nail polish remover. Its official name? Propanone. There's that 1 ending again.
So we know what they are and we know how to name them, but how do chemists actually make these things? Let's peek into the lab and look at a couple of classic chemical recipes.
First up is a go-to method for making aldehydes called the Rosenmund reduction. You start with something called an acyl chloride, you add a special catalyst, and you basically just swap a chlorine atom for a hydrogen atom. Boom! You get a clean conversion right into an aldehyde.
And then there's the e-tard reaction. This one is super cool for making those amazing-smelling aromatic aldehydes, like benzaldehyde. That's the molecule that gives almonds their signature scent. You take a simple molecule, toluene, add a reagent to it, and you create that fantastic almond aroma. Okay, so we've seen the chemistry, we've seen how they're made. Let's bring this all back home. Remember at the very beginning when I asked what connects flavors and plastics? Now we can finally connect the dots and see why these compounds matter so much. And this right here is really the key takeaway. Aldehydes and ketones are everywhere. They're the molecules that give our food flavor, they're the solvents that dissolve things, they're the preservatives that protect materials, and they're the fundamental building blocks for adhesives, paints, plastics, you name it. Our modern world is quite literally built with these things. So here's a practical question. You've got these two very similar families of compounds. If you had an unlabeled bottle in a lab, how would you figure out if you have an aldehyde or a ketone? Well, chemists have come up with some pretty clever and visual tests for exactly that. Here are two of the classics. Aldehydes will react with something called Tollens reagent. And what happens is so cool. It creates a beautiful, shiny layer of pure silver on the inside of the test tube. They call it the silver mirror test for a reason. Ketones? They do absolutely nothing. Same deal with failing solution. Add it to an aldehyde, and you get this brick red solid. Add it to a ketone? Nothing. These simple tests give you a clear, unmistakable visual answer.
So we've seen how the carbonyl group is the key to this whole world of aldehydes and ketones. But here's the thing. It's just one of many of these so-called functional groups in chemistry, which leaves us with a final thought. What other tiny arrangements of atoms are out there, quietly shaping everything from the medicine we take to the food we eat? The world is built on this amazing, intricate chemistry, and there's always more to discover.